right. What we have here. Which one would you like me to open first?
Just start with the Unit 5 review at the beginning. I think it's on the right side, and then
Number 1.
work through that. Yeah.
Let's download it. Maybe I want, yeah, that's good enough. I was going to say I can reduce it and give me more black space to write on, which I'm getting rather fond of. It shows up a little nicer. All right. So they want you to be able to do both long division and synthetic division when you can use synthetic division. You can't always use synthetic division. But if you're dividing by a linear factor, then you can. I don't think you can use synthetic division when you're dividing by a quadratic. All right, should we just start at 1?
Yeah.
What's the problem with that? Why does it need simplified?
The square root's on the bottom.
You cannot have a irrational denominator, and we do. Okay, in other words, I cannot turn that into a fraction or a decimal without approximating. So I got to move it to the numerator. How do I do that?
Would you multiply the top and bottom by 2 minus 7 root 10?
Yeah, the conjugate. That's called the conjugate.
Right.
And whenever you multiply something by its conjugate, then notice you're looking at the difference of squares factored. So putting them back together again is going to eliminate the root 10. Notice when you multiply those, you get, go ahead, do it. Hold on.
The bottom two?
I didn't mean to write 8 there. In other words, you can only multiply a fraction by the number 1, so that also has to be 2, like that. When you multiply the bottoms, what do you get?
So you'd pretty much like FOIL it, so it'd be 4.
And note that whenever you're multiplying by the conjugate, the next 2 terms are going to cancel one another, always, 100% of the time.
Okay.
So the only next term you need is the last. In other words, you can skip the O and the I of FOIL. So what do you get?
So you'd get
what is 7 root 10 times 7 root 10? First of all,
14 times,
not 14, but 10? 49.
Oh, right, 49 times 10, so 490.
So 490, exactly. And this has a negative sign in front of it. So it's that. So my denominator becomes a real number.
Right.
And that's what we're trying to accomplish. Now, in the numerator, I've got to multiply that. What does that produce?
So 16 minus, would you keep so you'd multiply the 7 times 8 and then just keep the root 10?
Exactly. Okay. Now, I can definitely reduce that, and I need to reduce it. Hold on a second. Let me erase some of this other stuff. Why do I know I can reduce that? For sure.
Because 2 goes into 16,
Exactly.
negative 486, and negative 56.
Anytime you can divide by everything by 2, you should do it. So let's start there. 8
Okay.
minus 28 root 10. I just divided the top by 2. And the bottom by 2 becomes minus 243. Now, that 243, hold on one second, excuse me.
Mm-hmm.
243 is divisible by 9. Hold on.
Mm-hmm.
Excuse me, give me a minute. One second.
Yeah, don't worry about it.
Sorry about that. I had something stuck in my throat. I had to go rinse my mouth out. If I'm trying to figure out if this is simplified or not,
Mm-hmm.
then I'm looking for numbers that divide into 243, also 8, also 28.
Right.
Now, 243 is divisible by 9 because the digits add up to 9. It's also divisible by 3 because anytime the digits add up to a number that is divisible by 3, that number is divisible by 3.
Right.
But neither of the numerators are divisible by 3 or 9.
Right.
So this looks like a final answer. Now, it's possible that they want all of their answers in this format, A plus BI. Is that true or false?
Yeah, that's true.
Okay. So this is not, no, excuse me, sorry.
I mean, the fraction, if you get it down to the simplified form, you can have the fraction form. I think that A plus BI is only for if it has an I in it.
Solutions only. Yeah, we'll get to that.
Yeah.
I saw that
Yeah.
and I got off track. This is a perfect final answer, what we have right
Okay.
here. Okay? We don't really need to simplify that. We don't need to separate it into that fraction plus that fraction. We could, but we don't have to.
Right.
If there was an I involved, then we might need to.
Then, yeah.
They generally like their answers in A plus BI format.
Mm-hmm.
And in order to get that, you have to separate that into two fractions. But as long as it's just an irrational numerator, then this answer is fine.
Right.
All right. How about number 2? What are we going to do? We may not need
So
to do all of these. As soon as you show me, you know how to do them.
Yeah. So 2, you'd multiply each top and bottom by negative 2/8 or negative 2 root 8. Sorry.
You know, I could, and that's correct, but it's actually I can do it a little simpler if I do this.
Oh, you just multiply by root 8.
Yeah, notice my only goal is to turn the denominator into a real number, not an, excuse me, a rational number, not a irrational number. And this will help me in the long run in simplifying it because the numerator becomes that, the denominator becomes that. So I have smaller numbers, and that is not a final answer. What is a final answer? What's root 8 equal to?
2 root 2.
So this becomes 18 root 2 over 16, and now I can simplify
and
that.
Then it'd be 9 root 2 over 8.
There you go. So it's amazing how some of these simplify. You wouldn't think Yeah, actually, that is kind of interesting that that's equal to that. If you look at
Yeah.
it, all the numbers are the same. You just move them around,
Yeah.
and it's a radical sign in there. It's like one of those Rubik's Cube type puzzles.
Hmm.
All right, now we get to some interesting ones. Okay, 3. Again, 3 is similar to 1 and 2 in that we got a problem in the denominator. You don't want an
Right. So,
imaginary denominator.
right, multiply by the conjugate, so it'd be 9i
Yeah,
on top and
and
bottom.
again, with this one, I could get away with just multiplying by that. And I'll show you why.
Okay.
You're correct. In general, you multiply by the conjugate. Here, I'm going to multiply by the conjugate. Okay?
All
But
right.
you want to do as little as you can in the way of, in other words, if I multiply by 9i, then I'm going to have to reduce 3 over 81.
Right.
And that'll be more math. Whereas if I multiply by I over I, that's still the number 1. I can multiply any
Hmm.
fraction by the number 1 without changing it. And that gives me an easier
3i over 9.
to simplify. Now, what's
Right.
I squared equal to? This is a big part of imaginary numbers.
Uh, -1, so it'd be 3i over just 9.
And now simplify that.
Um, it'd be I over 3.
Correct. And notice that that was much easier to simplify than if I had 27i over 81i squared.
Right.
Just because there would have been bigger numbers involved. So anytime you can accomplish your goal with a smaller set of numbers, you're going to be better off.
Right.
People make fewer mistakes with smaller numbers than they do with bigger numbers. Just
Right.
fact of the matter. So number 4, what are we going to multiply by? We won't necessarily do these. I want to make sure we cover everything on this page. So the moment you get it, I'll go on, and then if we have time, we can go back and
Yeah.
do some of these that we haven't done.
So for this one, could you just multiply by 8i on the top and bottom?
No, that won't get rid of the I in the bottom.
No? Okay. So you
Notice
multiply by 5 plus
what
8i.
happens if I do that.
Yeah. Oh, yeah, because the 5.
Yeah, you end up with 40i.
Yeah. So you multiply by 5 plus 8i.
So the only time I can take that shortcut that I took on the last one, if there's no real part of it. If it's just an imaginary number like that is, in other words, if there's no real part. Here we have a 5 with it, whereas there we didn't. So we were able to take that shortcut on 3, can't use it on 4. Whenever you have something that's in A plus BI format, and A and B are both integers, they're not 0, then you do have to multiply by the conjugate.
Right.
So what am I going to multiply by?
5 plus 8i.
Over 5 plus 8i.
Mhm.
Just let's do one more of these. Go ahead and do it. What's the numerator become?
50 plus 80i.
The denominator?
It'd be 25 plus 16.
Minus 64
Oh, no,
I
it's
squared.
64.
Remember, you don't have to do the 2 middle terms.
Mhm.
In other words, of the FOIL, you can do just the F and the L. The 2 middle terms always cancel out one another. So you can ignore them, and that's helpful because you can do it quicker. So whenever you're multiplying something by its conjugate, you can use that.
Mhm.
Okay, and what's 25 minus 64i squared equal to?
89.
I still have that. And it's fine to have an imaginary number in the numerator. Can't do anything about that, but you don't want it in the denominator.
Right.
And again, if now in this case, if they want it in A plus BI format, and they might at some point, what would it be? This is not A plus BI format.
Right. Would you move 89 up?
No, just separate it into two fractions.
Oh, okay.
So it becomes 50 over 89. That's the real part, plus 80 over 89, I.
Oh, okay.
So that is A plus BI format. And sometimes they might want that, but not always. You might get away with the answer that I have kind of double circled, my first answer.
Right.
That might be acceptable. I'm not convinced you would necessarily lose points unless they specified. If they specified, put your answer in A plus BI format, then you would want to do it for sure. Okay, number 5. The only imaginary number problems that are hard is division.
Right.
Everything else is very standard. Addition is easy, subtraction is easy, multiplication is easy. So let's do one multiplication. FOIL these two things.
All right, so you get 15 and then minus 15i. And then you get plus 15i. And then minus 15i squared turns into plus 15.
And notice here that the two middle terms also cancel.
Right, so it's just 30.
Yeah, which is interesting. I didn't realize that. In other words, that is not the conjugate of that. And yet we still have two complex numbers where the middle terms cancel. So it's interesting discovery. I didn't realize that. I wonder if that's always the case as long as those two numbers are the same and those two numbers are the same. It is the case.
Probably, yeah.
Yeah, no, it is going to be because that will always cancel that as long as they're opposite signs.
Right.
Okay. How should I write that?
So it's 49, and then
Let's just write it. If you can write it for me, we'll go on to the next one.
Oh, just it's -7 plus 6i, and then in parentheses -7 plus 6i.
Yeah, I know you know how to do that. So that's the only thing questionable on that. Okay, let's do number 7. A little different.
Okay, so plus I minus 4. So you have to multiply the first pair and then the second pair.
Yeah, you got to
distribute
each of these monomial terms.
So it'd be 36 or 32i, and then plus or minus 40 or plus 40.
You know what? It never hurts to do that step.
Okay.
Problem is when you try to do multiple steps at once, you really introduce greater opportunity to make mistakes. Now we can certainly change it to that, but I like doing it in 2 steps, and I'm a person that likes doing multiple steps at once. But I still think you're better off not doing it. You'll make fewer mistakes. And what is this part here?
So that's -4i minus 8i squared, or plus 8.
Okay, you're comfortable enough with that okay, I'm fine with you doing that in 2 steps or in 1 step. Now, add those two together.
So it'd be 28i plus 48.
Now put that in A plus BI format.
Just 48 plus 28i.
Always depends on the student. Some students can do multiple steps in their head, others can't. As long as you can do it, I won't interfere with it. You know how to do this one, I'm sure. Let's go on. Is there anything in number 8 that gives you pause?
No, it's just pretty much the same as number 7. Just
number 8 might be tough if that was a negative sign.
Yeah.
Because
well, then you
would
get
have
the 2 parentheses and just make the rest of them
everything.
Yeah.
That's the only time that those are problematic is when you have a negative sign. Not everybody remembers to distribute that negative sign to everything. All right. So we're looking at number 9.
Yeah.
X cubed plus 125 equals 0.
Right. So
how many real roots?
How
many real roots does it have? I know the first
3
has how many complex roots. Well, if I try to solve this, I get x to the third equals minus 125. And then only,
no, it has.
That's only one answer.
Yeah.
Now, I could have of multiplicity 3. You familiar with that term?
Yeah.
Okay. And turns out that I do have multiplicity of 3. Because
you can cube 125.
Well, I can make x cubed be x times x times x equals minus 125. So I think that has multiplicity of 3. Hold on a second. Let's back up. Because this is actually a fairly sophisticated problem. If I treat this as the difference of perfect squares, or excuse me, the sum of perfect cubes,
Yeah.
how does it factor?
It's into, I think this is written down somewhere. There's an equation, it's like a plus b equal, and then parentheses, a squared minus ab, or a squared plus ab plus b squared.
Which works out to be this.
Yeah.
Okay. Now, clearly we have 1, and all of that equals 0. So clearly this gives us x equal 5, or negative 5, but that's 1 of multiplicity 1, not 3. And then this gives us the other one.
So you probably end up with 2.
Well, I think this is going to give you complex solutions. How can we tell really quick? What's the quickest way to tell?
I would just use the Pythagorean theorem.
Not the Pythagorean theorem, the quadratic formula.
Right.
But you don't even need the whole quadratic formula. The only part you really need to analyze is the discriminant.
Right.
Because this is the discriminant, okay? And if that's negative, that's 2 complex solutions. If it's positive, it's 2 real solutions. If it's exactly 0, it's 1 real solution. So that's going to help us answer question A as to what the discriminant is. Well, the discriminant is 125 squared. That's negative b squared. Or that's b squared. minus 4 times 1 times c, which is 125 squared, right?
Yeah.
Is that a positive or a negative number?
So negative.
Ah, that means these two solutions are complex. So the answer is 2 to that.
Mm-hmm.
The possible number of real roots.
3.
No. And here's the reason why is that this is a cubic. A cubic has at most 3 solutions.
Oh, so
well,
1 then.
Just found 1 real and 2 imaginary. So the possible number of real roots has to be 1 for this function.
Yeah.
For this particular function. Now, it's not 3 because you really have to figure out all 3 solutions, and we've already found out that 2 of these are complex, and there can be at most 3 solutions. So, and we found 1 real and 2 complex. So we have all of our solutions. We know that there are precisely 2 complex and 1 real. I'm not sure why it says the possible number of real. That confuses me a little bit. Why they don't just say the number of real.
Right.
I'm assuming that they're referring to this equation only. Now maybe things will be different when we look at number 10, but okay, the possible number of imaginary roots. Wow, I'm really confused now. We just figured out that it's 2 for number 9.
Yeah.
Find all roots, we've done that.
Yeah.
All right, let's look at number 10 and see if these words make more sense. Let's see, we got 3 and 4. Is this a quadratic in disguise? Yes, it is. Do you know what I mean by a quadratic in disguise?
Kinda.
This is a quartic.
Mm-hmm.
But if I were to go up here and I were to say, let's let u equal x squared, then what am I looking at? I'm looking at u squared plus 9u plus 18 equals 0. If I can solve that, then I'll be well on my way to solving for x. And I'm sure you've discovered by now that solving anything higher than quadratics can be extremely hard and complicated.
Yeah.
When you have to use the rational factor theorem or anything like that, it's a nightmare in terms of how long it takes to solve for it. So if you can take a quartic and make it look like a quadratic with this, what is called u substitution, you want to do it. Because even though I can't factor that, yes I can. How's that factor?
When
it's in u.
U plus 3, u plus 6.
So, and now I go back and I resubstitute. So it really factors into x squared plus 3 times x squared plus 6. What does that produce? What do I do next to solve for x? In other words, I'm going to answer all 4 of those at one time.
Well, so do you make them? Do you put both of them equal to 0?
You do. So you get x squared equals minus 3. What's that solution?
I root 3.
First of all,
Plus or minus I root 3.
very good. Everybody leaves the plus or minus out. Whenever you are solving an equation by taking the square root of both sides, always begin your words with the words plus or minus.
Yeah.
The only thing I know how to tell people, because it's the hardest thing there is to teach people. I guarantee I've been tutoring for 8 years, and that's the most common mistake made, is they leave out the plus or minus. And then it's square root of negative 3, which is what?
Square root of 3. Square root of negative 3.
Square root of 3i.
Oh, right.
Because here's the thing. When you take the square root of a negative number, here's the way to always figure it out. Separate it into that times that. Okay? That's I. So you end up with the square root of 3i. Make sure the I is outside the radical sign.
Right.
Well, what's this solution? If this solution is plus or minus square root of 3i, what's this one going to be?
Plus or minus the square root of 6i.
So now, how many complex roots do we have?
4.
With a possible number of real roots. I don't know why they put that word possible in there. Why not just the number of real roots? 0.
Yeah.
The possible number of imaginary roots. 4.
4.
Find all roots. We did that.
We did. Yeah.
Now, why would they put it like that? What are they looking for? I'm trying to figure out. Are they trying to elicit some understanding that I'm missing here?
I don't think so.
I can't.
Because she said like, if you have a really big one, you can say like.
This seems very strange because those two things seem like the same question to me. And maybe they're not. Maybe they're not. Maybe there is a way to immediately figure out the possible number of imaginary roots, and then you narrow it down to the number of imaginary roots. But first of all, complex means the same as imaginary.
Yeah, but you can figure it out like there's 4 possible like real roots for number 10, and then there's 2 possible imaginary roots for number 10 without solving for the x's.
Okay, maybe that is what she's getting at.
Yeah, maybe.
Okay, I think you're right. That's the only thing that makes sense. Because there would be no other reason for wording it the way she did. So in number 10, the complex roots are 4. Possible number of real roots would be 4. The possible number of imaginary roots would be 4. Find all roots, we did.
Would it be 2 for imaginary roots? Because like if you have
down 4, there's 2 there and there's 2 more there.
Right. That's true.
Imaginary roots always come in pairs. Always.
Yeah.
You never find one imaginary root, ever.
Right.
So when you have an imaginary root, you got at least 2 of them. And here we have 2, so we have 4.
Yeah.
Okay. So I'm still a little confused, but I tend to think that these are better answers. You know, I think what these questions mean is if you have a cubic, you can have 3 roots. If you have a quartic, you can have 4 roots. If you have a 5th degree polynomial, you can have 5 roots.
You can have 5.
You can only have as maximum, you can only have the number of roots as the maximum degree of your polynomial.
Right.
And I think that's what she's asking there. I'm not sure.
Yeah, I think so too.
Because
I think that's what she's saying.
A little strange, but I think that's what she's meaning.
Yeah.
Do you have an answer, Key?
Yeah, I can probably find one. It's like,
Might be worth looking. Even if you have odds only, number 9 would tell us the same thing.
yeah, this isn't due. This is just because we have our test this week. So
Okay. I'm still kind of curious as to why these are worded so strange.
yeah, 4, 5, 6, 7, 8, 9.
If you have an
Yeah,
answer
it says.
for 10, what is it?
Yeah, for 10 it says complex 4. You can have 4, or she says you can have like 4, 3, 2, 1, or 0 real solutions, and you can have 0, 2, or 4 imaginary solutions.
That's what she's getting.
That's what she's getting at, yeah.
In other words, she's letting you know that imaginary solutions come in pairs.
Yeah.
And real solutions, you can have any of these. Any of those combinations. Okay. And then we did find all of the roots. So we did that part. It was just the wording of B and C that had me puzzled. Now I get it. All right, let's look at number 11, if I can make it out. I can.
Number 11. I think it's just the same thing.
Let me rewrite it. Well, this is not quite the same thing because it's a quintic. And those are not going to be easy. Let me just write it so I can read it without squinting.
So
okay.
You could have 5 complex roots.
They give you 2 of them.
Yeah.
I guess that's what that means.
No, it says one factor has been given, find the other roots.
One factor has been given.
Yeah.
Okay. Let's talk about that for a second. The difference between the roots and the factors. If I tell you x equal 2 is a root, what's the factor?
X minus 2.
Okay. So they're telling us that one of the factors is x plus 1 minus 3i.
Yeah.
Which means that if x plus 1 minus 3i, that tells us actually 2 factors, right?
2 roots, yeah, or 2, yeah.
What's the other one?
X minus 1 minus 3i?
I think it's this.
Oh, right, you don't change, yeah.
Well, here's what I know. I know that, let's say that the 2 roots were this. They're always going to be conjugates of one another, okay?
Yeah.
So the factor for this one would be x minus, in parentheses, 1 minus 3i. And the factor for this one would be x minus 1 plus 3i.
Yeah.
Turns out that that actually becomes x, if I remove the inside parentheses, x minus 1 plus 3i. And this one becomes x minus 1 minus 3i. Right. So when you're trying to figure out the conjugate, the x minus 1 doesn't change. What changes is the sign on the I.
Yeah.
So that's why when they give us one factor, I know the other factor, I won't call it the conjugate, but I know the other factor has to start out like that.
Yeah.
And then I got to change the sign on the end part only. So those are two of the factors. And they are in factor format, not solution format.
Right.
So what's my next step?
So for A, you'd be 5. For B, it'd be
Hold on.
1.
First of all, complex roots always come in pairs. Can there be 5?
Oh, so there'd be 4.
We don't know yet. It's all we've done is found 2. How are we going to figure out whether we're looking at 4 or 2?
I don't.
Got to do the division.
Right.
Now, it seems to me this is an awfully tough problem. Let's see, we got 20 minutes. We might be able to finish 11 and 12.
I mean, I know how to do the. I know how to do the division pretty well. We went over it a lot.
Even with using, you're going to do it synthetically?
Yeah. Yeah. You could. Or
It's the best way to do it. I'm not real sure how to do the division with long division. When you're dividing by complex factors, the best way to do it is synthetically. Let's just go through at least one synthetic division. And all I have to do is put 1. I know that my roots are 1. Well, what is my root? If that's my factor, then my root is x. Remember, you have to put the actual 0 in the box when you're doing synthetic division.
Right.
So what is this? If x plus 1 minus 3i is the factor, what is the 0? I shouldn't really call it the 0. I should call it the root. Because it's improper to call a complex number a 0 because it doesn't really cross the x-axis. So it's a root, but it's not a 0.
It'd be -1 plus 3i. Or -1 minus 3i.
No, I think you were correct the first time. If that's the root, then does that,
right, because
I got to take x minus that, always putting parentheses in there, and that turns into x plus 1 minus 3i, which is what we're looking at.
Right.
So that does match the first one, which means what goes in the box is -1 plus 3i.
Right.
Goes across the top. You know, hold on a second. So this one becomes, the reason I said that is because I'm going to need space to write, because you have to do 2 synthetic divisions to get down to a cubic. And you got to get this thing down to a cubic before you can go forward. And in order to do 2 synthetic divisions, you kind of have to do them at the same time. In other words, you have to do one and then immediately do the other.
Yeah.
So I need room to write. So let me make sure that that is that. So those are the 2 things, -1 plus 3i, -1 minus 3i. First of all, do this. Scroll up, take another picture. So I've got -1 plus 3i and -1 minus 3i. Those are my roots. So those are what go in the box. Start with the first one. Goes across the top.
1, 4, 24, 40, 100, and then 0.
And you know about, ooh, yeah, I guess you do need the 0 there. So I was going to ask you, you know about if you're missing one of the degrees, you have to put in a ghost variable with 0.
Yeah.
All right, now this is a little tougher synthetic division. Tell me what to write. I know you can't see where I'm pointing, but I know what I'm talking about.
So you bring the 1 down, and you multiply that by -1 plus
Whatever's
3i.
in the box, so that's what?
Just -1 plus 3i.
-1 minus 3i.
Minus 3i.
Whoops.
No, yeah, it would be.
No, you're right. It's plus.
Yeah.
Okay. Now add those two. That's why this gets complicated. I'm going to use parentheses just for separation purposes.
Yeah.
How do you add a real number to a complex number?
You add it to the real part of the number. Right?
With me so far?
Yeah.
Now multiply that times that.
So -1 plus 9.
Hold on.
Or -1 minus 9.
Well, just a second. We're multiplying this times this.
Right.
Okay,
so -3.
Gotta FOIL it.
Yeah.
Keep going.
Plus 9i squared. So minus 9.
Hold on. Yeah. See, that's the only problem I have when a student does things in a different way than I'm used to, is it's hard for me to follow it. FOIL.
Right.
Use FOIL. That's the best way. I hate to really mess with what you're comfortable with because you're very good at it. But if I'm multiplying this, I'm multiplying that by that, and then I'm finishing the -1.
Right.
Then I'm doing the next term by that, and then I'm finishing the 3i.
Right.
In other words, I'm always going left to right, and I'm finishing everything on the left before I go to the next term.
Right.
And you might think that, well, that's completely unimportant what order you do, and you're right in a sense, but when you start multiplying trinomials by trinomials, then it's very important that you follow a pattern because it's really easy to forget one. So I don't even use the word FOIL. I use ET, every term by every term. That's what you're doing, whether you're multiplying a binomial by a binomial or a trinomial by a trinomial. You're multiplying every term by every term. And when you do that, you want to follow a certain pattern, because if I'm doing a trinomial by a trinomial, I got 9 terms. I want to make sure I don't get out of order and skip one. So I truly believe that that method's going to serve you better than what you're showing me. I understand it doesn't make any difference, but it might when you get to trinomials.
Yeah, I got you.
Okay, so what do you get here?
So you get -3 and then -3i. And then 9i.
Plus 9i. You need the plus sign.
Plus,
because we're part of a
9i.
polynomial. Yeah.
Plus 9i squared.
Okay. Simplify.
So -3 Plus 6i minus 9.
So minus 12 plus 6i?
Yeah.
Okay. So that, wow. That's why I said when I looked at the clock, this is going to be a long problem. So
Yeah.
that is this answer right here. Minus 12 plus 6i. Now you got to add those two numbers. And I'm going to have to start writing smaller, I can see. What do you get when you add those two numbers?
You get 12 plus 6i.
You get, first of all,
Oh,
you
wait.
add the real parts. Oh, excuse me. You're absolutely right. Okay, sorry.
No.
Do that negative sign for a moment. Now, we could spend 20 minutes finishing this problem. We don't have 20 minutes, so let's just talk about what we're going to do. First of all, what's the remainder going to be?
0.
Yes, has to be. If this is a factor, and they've told us that that is a factor.
Right.
Okay, so once I finish this division, I'm going to have all these weird imaginary numbers on my top row. Well, guess what? Those will all disappear when we do the second part of this. In other words, I know I'm going to get a 0 remainder, and I'm going to get a big complicated answer here. Then I'm going to do it again. And in the box this time, I'm going to put minus 1 minus 3i. I'm going to go through that whole procedure, and assuming I only have 2 complex roots, then this is going to eliminate all the i's, and that will be a cubic. And I will still have a 0 remainder. Are you with me?
Yep.
Okay. Now, that cubic, we have to kind of determine how many roots it has and whether they're real, or that could still have 2 imaginary roots. So in terms of the number of complex roots, I know it's at least 2, but it could be 4.
Yeah.
And I won't know until I go break down that cubic, which I would do other than it'll take me 15 minutes to even get to that point. So you seem like you really understand this. Let's just talk about concept. So I'm going to have a cubic, and I assume you're familiar with the rational factor theorem?
Yeah. Probably just not
factor theorem.
by name, but
If there is a rational factor to a higher degree polynomial, doesn't matter whether it's a cubic, quartic, quintic, whatever, if there is a rational factor, then it will be P over Q, where P are all the factors of the constant, and Q are all the factors of the coefficient of the highest degree.
right.
In other words, if I had a 12 as my constant on that cubic that I end up with after dividing by both of these imaginary solutions, then I can begin the process of searching for more zeros. And
Right.
I'm sure by now you've seen how problematic that is. That's almost a 15-minute problem in itself.
Yeah.
Because you have to test all possibilities where P are factors of the constant. Well, if that happens to be a 12, then I got 1, 12, 6, 2, 3, and 4, and each one of them is plus or minus.
Yeah.
And the denominator, if that's a 1, then at least there that's only plus or minus 1. But you still have those other 8 factors, and you need to test each one of them until you actually find one of the factors.
Yeah.
Once you find that, you go ahead and do another synthetic division, come up with a quadratic. In other words, let's assume you have one rational factor here. That's going to leave over a quadratic. Once you get it down to a quadratic, you can determine whether that has 2 complex solutions, 2 real solutions, or 1 real solution. If you find it has 2 complex, well, then you will know you have 4 complex solutions. If you find it has 2 real, then you'll know you only have 2. So to answer question A, takes about 20 minutes.
Yep.
And you have to know what you're doing. In other words, it's not just 20 minutes of rote work. You have to really understand this stuff. And this is pretty complicated stuff for PreCalc. I don't think PreCalc gets any more complicated than this.
Yeah.
I assume the possible numbers are 5, 0, 2, or 4.
Yeah.
One factor has been given, find all of the roots. So you are eventually going to reduce this to a cubic. And depending on that cubic, there are some cubics that can be factored easily if they happen to be subject to grouping. You know what I mean by that? Those are the only cubics that are easy to factor, the ones that are you can factor by grouping. Any other cubic, you got to use this rational factor theorem, P over Q.
Right.
And that is a hard, long process. And that just finds one factor, which you then have to divide into your cubic to get the quadratic that's remaining. And then you have to examine the quadratic to see if it has 2 real solutions or 2 imaginary solutions. That's the only way you're answering all of those questions.
Yeah.
Sorry we didn't get to do at least one of these that required the rational factor theorem, because that's really an amazing thing, that you have to solve cubics by that thing. Most algebra students would tell you, oh my God, the quadratic formula, are you kidding me? It's too hard. Wait till they get to cubics. There is no such thing as a cubic formula.
Yeah.
The way to solve cubics and above is by this rational factor theorem. And it is super hard and super complicated.
Yeah.
And requires a lot of synthetic division. So, anyway, Hayden,
all right, cool.
Seems like you know this stuff pretty good. I'm impressed.
Thank you.
But good luck if you have a quiz coming up. And otherwise, I will talk to you next time.
Awesome. Cool. Thank you.
You're welcome. Bye-bye.